coded that's here. Next one is sort of this. I don't know. The last thing I remember the minute I'm like, well, look at this. Yeah, I was like, yeah. That's it. My syntax was so strange. It was just big code that was software. Without you coding from the spirit of the UTS stuff. You can still know what I'm so I got to see this. It's valid. I know this is it's over 5 years. Until I place this all on this. You got so is that the right? Just have that sure. Leadership. Keep that back on. But you can say that it's not later. Big amount is there. Okay. One of multiple twists. That's another knowledge thing. I'm just everything. Yeah, but it's honestly. So everything is I was. I used to I went to
Okay. Hello, everyone. I hope you guys are mostly done with the midterm season. So what we discussed last time and the previous 3 lectures was something related to real-time operating systems, which you also do currently in Lab 2 and the project. We discussed the theory, well, scheduling, why do we need it, some of the scheduling algorithms, and we went through some examples. And today's tutorial in the morning kind of give you a couple more examples. My suggestion is try to walk through these examples yourselves, especially the ones in the lecture and the tutorial. If you have any question, let me know, right? And then we can follow up on them, right? What I'm hoping for is that in the last lecture, hopefully in the semester, we would have finished the material already, and I can spare this lecture to, well, take questions and maybe solve more examples related to scheduling. But to be able to, well, leverage this this lecture and coming tutorials as well, you need to walk through the examples yourselves to see what questions you have, right? So my suggestion is take the tutorial, previous lecture slides, walk through the examples. If you have questions, let me know, let Ali know, let any of the TA knows, and we can help you, okay? So these things are not easy to get unless you really do it yourself. What we're going to cover next is something very related to this scheduling and real-time operating system theory. In fact, one of the reasons why we had the RTOS lectures is exactly for that purpose, for real-time systems, which is we need to basically analyze, let me see. We need to analyze the tasks. Remember in the introductory, are you able to hear me well? Is that okay? Get this a little bit closer. Just let me know if I'm not able to hear. So the reason why we discussed real-time operating system scheduling, or if you remember what even we need an RTOS, general purpose operating system, Linux, for example, or Windows or Android, is we need strict timing guarantees, right? That's the main purpose why people use RTOS in embedded systems and not something else. Because RTOS is easier to analyze, it's more strict in terms of timing, and it's why it should be used, right? So now, given that we have scheduling, we have RTOS, we need to do the purpose of the RTOS, which is analyzing the task time, right? So be able to guarantee a worst case execution time on the tasks that we have to run. Otherwise, using RTOS is useless, in fact, right? If I'm not able to guarantee this time. So this is what we're going to discuss in today's lecture. So if you remember just quickly, we introduced a task model. Well, the simple one is a periodic task model where every task is being defined by 3 main metrics. D, which is the deadline of the task, C, which is the computation time of the task, or we said this can also represent the worst case execution time, and T is the period. And then we said for every period of the task, we call an instance of the task a job, right? We release a job of that task, and every job is exactly identical. And then the job takes T time to run. For example, this is job tau I0 from task tau I, and then it runs for 3 time units. This is why CI here is 3. And then the deadline is 8 in that case. Then in the next period, a new activation happens, a new job is being released. It takes exactly the same C, which is the worst case, 3 time units. They don't have necessarily to be contiguous or back-to-back, they can be split. Can you give me an example why in one instance those can be really back-to-back, while here the second job has to split there? What do you think? Why this might happen in the other? That's a possibility. Can interrupt happens? Yeah, that's a possibility. What else other than interrupts? What else did we discuss? Yeah.
Like a variable that's stated is in another task.
Yeah, shared. Yeah, well, when you mean shared resource in general, can be actually another task. That's also a possibility. There is another possibility without shared resources or interrupts. What do you think? Something we discussed in today's morning tutorial. Well, the system is not running a single task, right? So at one point, the scheduler might decide, for example, I'm running EDF, and after running this for one time unit, the scheduler EDF, for example, decides I need to switch to another job, right? So you switch to another job to run it for 2 time units and then come back, right? So maybe you get preempted not by an interrupt or by shared resource, but you get preempted by another task because of the scheduling, right? All of this can happen. But what is important is, or what we guarantee for that task, if this task set is schedulable, is I can finish for every single job all the computation units before the deadline arrives, right? This is the strict requirement that we want to do everything for. If we cannot guarantee this, well, we don't have a real-time computing system, and there is no guarantees. We cannot really, well, drive that car safely if the airbag is not really guaranteed to be valid, right? Good. So for that purpose, we are going to discuss what we call worst case execution time analysis. So we already modeled the task by deadline, period, computation time. Our condition for guaranteeing the timing requirement is that always, all the time, the worst case computation time or the worst case execution time has to be less than or equal to the deadline, right? Otherwise, again, you lose your requirements, there is no longer guarantees. We can think of this WCET, or worst case execution time, as an upper bound on the computation time C in the task, right? So that's the worst case instance, the worst possible scenario that this C can run, right? And in fact, there is a whole industry, especially automotive, avionics, etc., into how to obtain this worst cases. It's very hard to obtain, right? Good. So just to have a feeling of what does this really mean. So by being able to guarantee this, I'm answering the questions, well, in my car, for example, will my brake-by-wire system actuate the brakes within 1 millisecond? For example, if I hit the brake or it's still driving cars, so the brake has to be hit by a wire, not by a human. Will this happen within 1 millisecond? Why? Because maybe you have been steady in front of you, right? So this 1 millisecond is going to be your what this 1 millisecond mean? Model 2 in our model. What do I call this one? The red line of the task, right? And then to be able to guarantee or answer this question, you need to calculate WCET, make sure it's less than 1 millisecond, and then if it's less than, then you are good. Otherwise, you need to redesign the system. Another possibility is, for example, maybe if you have a camera-based, well, self-driving car, steered by wire system, can I identify a bicycle crossing within 100 minutes, right? This is basically object detection, right? So you still have a deadline here, 100 milliseconds. Well, basically that's assuming you get raised 10 hertz. But then in a drone, for example, will my drone be able to finish computing control commands? Like, for example, I'm sending a remote command that, well, I need to change direction or, go down, go up, or changing basically all like or whatever control command you are sending to your drone, something similar to what you have been sending through the terminal to our car. Will the drone be able to respond and act upon that command within, for example, 10 milliseconds, or here is 100 100 hertz, assume that your feedback loop is 100 hertz, right? So all of these are in fact different, representations or different examples of how deadline is important to guarantee in different systems. Think of if the answer of this question, any of this question is no, what is going to happen, right? For example, in a drone, you don't respond within a time, then the command is not being executed. The drone might crash into something and get destroyed or hurt someone, right? Maybe in the car, for example, you hit the bicycle. Well, too bad. Or in the brakes, again, you're going to hit the brake and you go into a wall, right? Or you cross a red line, a red traffic signal, right? So all of these things, the consequences are too bad, right? And this is why we need to guarantee that the deadline under all circumstances, in worst case, is met. How to do it? Well, this is basically the topic of today's lecture. So in worst case execution time analysis, or in general in timing analysis, there are three definitions of an execution time. We have what we call WCET, which is the worst case execution time. This is mainly what a real-time system or a certification-based system is concerned about, because you need to design for the worst case for safety reasons. There is also the best case execution time, and there is the average case execution time. I already told you that safety critical systems care about WCET. Nuclear reactor, a drone, a healthcare system, whatever. This is the system that is safety critical, care about WCET. Who cares about average case? You give me an example of something that the average execution time matters. We already discussed these things before a few times. Well, laptops you have in front of you right now, right? So you care a lot about response time, right? I want to run as fast as I can. This is your average. If at one point your laptop, takes a lot of time to run one application because it's low in battery or because you are running hundreds of things, so you are playing every game, well, it's okay, right? If you have it once, amazing. As far as the average case is fine, right? So average case is just general purpose system. And we differentiated between, so in lecture 0 and 1, we put multiple definitions of embedded systems as opposed to general purpose systems. One of them was what metric do you care about? We said mostly embedded systems, especially safety critical ones, care about the WCET, the worst case scenario, while average case is more of a concern to the general purpose systems, right? And then we talk one step further and said in modern embedded systems, and we give the example of modern automotive, for example, also average cases of importance because we have what we call a mixed critical system. So in the same system, you have, a hard deadline, a hard real-time task, we call it hard real-time, and we also have cases of high criticality, engine control, airbag, cruise control might be, and then we have also infotainment unit, GPS, reporting or logging tasks. All of these are kind of average case, and they care about average case performance. And the challenge is you need to accommodate for both. Why this is a challenge? Because we also mentioned that in fact all the techniques we have in systems, modern systems, have a tension or a trade-off between these two. Like most of our laptops are designed for average case, and hence, in fact, they are not good for embedded systems real time. Why? Because they don't have any guarantee, right? In fact, if you run any application in your laptop, there is no strict guarantee that you are going to finish in 1 minute, right? It depends on so many things. What is the status of the operating system? What stability is being deployed, which is not real time? How many other applications are competing with you? What is the power status of the laptop? All of these things creates a huge amount of variability that is not good for real time. So if you design your system for average performance, it hurts a lot the worst case execution time. It hurts analyzability, which is not good for embedded systems. On the other hand, if you design your system strictly for real-time embedded systems, then you care more about the worst case execution time. But on the other hand, your performance will be hurt a little because you have to make design choices that favor this worst case instance. On average case, you might be paying performance penalties, right? And this is again one of the existing problems that is very hot in terms of research and industry as well, especially again for mixed critical systems where I need to account for both, right? Good. So one way to visualize these metrics is to look into execution time as some sort of that graph. One question to you to understand what this graph is why execution time might have this variability. So what I'm telling you right now is for one task, exactly the same task or the same application, the execution time is not the single number. I'm not saying, for example, this task will take, well, 1.5 million cycles or 1.5 million nanoseconds. But instead, it will take different execution times at different indices. Why this might be? What do you think? Why do you think a task execution time is C in our task model is not in fact one number, but instead, well, a spectrum of numbers that we have to count? Yep.
Depend on the environment, if it's the temperature and stuff, and then it's not really.
That's a very nice thing. Thanks. Yeah, thank you. And this in fact, I wasn't thinking this when I asked you that question, but that's very valid. So basically, there are also factors that impact, well, the electronics of the system itself, right? Especially in these systems. Think, for example, of those that will go to a spacecraft, right? Which is one of the most certified systems in the system. Like, for example, there are certain FPGAs that has to be hardened, called hardened industry, that you have to go to space, which means they have to operate without any intervention for a few number of years, usually 10 to 15 years, and you want to make sure that they will not be impacted by being hit by electrons or photons or changing temperature, and then you have to certify them using temperature ranges. Why? Because actually this is being discussed in electronics course, but in fact, operating in a certain voltage, like it's not guaranteed for electronics, because based on what temperature you're operating at, if you open, for example, any of the data sheets we have, including the SMU6X, you will find that there is an operational, what we call operational conditions. Like it tells you, I give you this error within this temperature variability, and I give you this temperature variability. And usually it's being tested labs before the product is being released. So this variability is a factor, excellent, especially for embedded systems. What else? What do you think? To think of what is this task is in reality, right? Like there is a task that's, for example, in a car, takes data from a camera, has to process it, and then take an action, right? Is there any variability in the example task I gave you? What do you think? Well, this camera is not capturing a constant picture, right? So I'm going into the street, I might be capturing a human being, I might be capturing a tree, I might be capturing a traffic sign. So the input itself that the task is supposed to process, the input will differ, right? Why this matters? Why you think if I change the input, the decision time of the task might change? Yeah. Exactly, thank you. And can you take this thought a bit further and say, give me examples from source code, so like Steam sequence examples, any other byte, how this might happen within a tool that if I have a different input, I might process it differently based on different things.
Yeah. Example of the camera. Products. If there's like a pedestrian that's big, has a stationary object, also maybe needs to be more. Processing those things.
Yeah, correct. So basically, to generalize that question or generalize this answer, our programs are mainly composed of what we call control paths, right? So we have if statements, we have for loops and branches, and based on the status of your variables at this one-time instance of the application, your if condition might be true or false, right? And then I might take the if or the else, or I might be ending my for loop or continue the iterations, right? So all these things depend on the input, right? And this impacts so many things. It impacts programming, it impacts compilers, it impacts operating systems, because based on what path I take, well, my application is not in fact one possible flow, right? One possible critical path. It might end up being different paths based on what is the input, right? And being a different path, for example, based on certain condition, maybe call it a function, or maybe based on that exact same condition, if it takes a different value, I call a completely different function. So if I want to analyze how many cycles, how many instructions I'm executing the application, well, I need now to account for these 2 possibilities, right? Or 3 possibilities, or 100 possibilities, I don't know, right? And this is why, in fact, timing analysis of code is a very, very hard task to do, right? There are many companies that are specialized only in analyzing software to guarantee execution time. By the way, one of the things that I don't even know, McMaster is the only university in Canada that has this software certification center, which is part of our CS department. Well, it's a huge center that has a lot of collaborations with automotive and well, nuclear plants and avionic companies. The only come, here is my software, please analyze it to me to give me some sort of guarantees for certification, right? So it's an industry on its own, being able to analyze your application. Why? Because our applications are not a single 10 instruction program that is just procedural, right? Composed of tens of thousands, if not millions of lines of code. If you remember, I gave you the example of Mercedes-Benz and the F-22 in lecture 1, right? I told you it's millions of lines of code, and based on what is my input, I have many control paths that I need to analyze, which is not very easy. Good. So for that purpose, well, the variability of the execution time is huge. The good thing is that you don't really need to analyze every single instance. Well, you might be able to do different methods to be able to. What I'm looking for from a real-time perspective is not to say, okay, at this moment of time or at this input set, my execution time is milliseconds, right? What I care about the most is, in worst case, my worst case execution time will never exceed, for example, 2 milliseconds. No matter what is the input, no matter what is the temperature, the variability, the environment, anything, no matter even what other tasks is running with me, my worst case execution time is 2 milliseconds. And hence, well, does this really meet my 10 millisecond control loop or 10 Hz control loop requirement or not? If it meets, great. If not, then I need to redesign something, either the hardware or the software. Good. So this is basically the worst case execution time is this instance here, which is the worst possibility. The best case execution time is the minimum execution time in this spectrum. And then the average is basically the average of this number. If I have it here or not. So one other good thing about this graph is based on what method you really follow for determining the worst case execution time, you might have different points. What do I mean? For example, there are 2 big classes into how to obtain this worst case execution time. The example I will just explain to you right now, which is look into all your control paths, analyze it. This is called static time analysis. There are tools that do this, commercial tools and companies that do this. But as I would also say, if the code is very complex, this task is the very tedious. Well, in fact, if I think about, well, to its high terminology, it's an incomplete problem. It's not, in fact, guaranteed that for any program set, I will be able to analyze all these facts, right? If you guys had a compiler, it would be easier to explain because in compilers they're also related to how to analyze the application different paths. But that's a different story. So I might have an example later on to literally imagine how this is hard. But for now, trust me, this is basically very, very complex. Good. So I might be able to do it for easy tasks, but not for a very complex one. What Ruby really does, because we still have very complex tasks in every single realistic embedded system. What they do is they do what they call empirical time analysis, or measurement-based time analysis. They say, well, to satisfy those certification requirements, what do I do is I take my task set, I take my hardware, my card, for example, and run it for millions of times with all possible mediums, right? Like think of, you might have heard in the news that Google card has been around in the space for 10 years right now, collecting data and doing testing, etc., etc. Why? Because you want to test it for different environment setup, well, raining, snowing, clear, different temperatures, different places, different traffic signs, different regulations. So the more testing you do, very good. Right now, I'm not really taking a task, sitting in a room or a desk, and trying to analyze my application. You see, I'm having it in the field, collecting data, analyzing how do I act, fix myself, do it again and again and again. So, and then if I was able to tell the certification authorities that I did run this task for 10 million times with all these input sets, and I'm guaranteeing that there is some coverage that I have covered 99% of the cases. And plus this, I'm adding a safety factor of 15%. This is what we will do in avionics, right? Then, well, they will say, okay, we did your due diligence. Well, this is safe enough to have it, right? So people go for the measurement based or empirical based because static based is very tough. But the point is that in empirical based, you might end up with different numbers based on how many tests you do run, right? This is why you find here, well, this is the maximum observed execution time. Why I call it observed here? Because this is something empirical, right? I run, I measure, this is what I observe, right? And then afterwards, you see here that this, well, my upper bound is a little bit higher than the worst case execution time. Why? Because I add a safety factor just to make sure I also, any case that I then account for, I'm already taking it further, right? Most certification authorities ask the companies to add 10-15% safety factor on top of what they come up with. Okay, so again, in a worst case execution time analysis, given a code, I want basically to, well, analyze how many instructions I run, how many cycles they take to run, and then this will be my computation. Doing static time analysis, which is the one that is basically more theoretical, or, well, you don't do it empirically, but rather do it by analysis with verification. You can assume that your static timing analysis tool is a black box that takes two inputs. Your code of the task, which is just simply the software, and the hardware itself, the architecture that is going to run on, which is a model. Basically, you build a model of your hardware. And then the tool itself will run. Run means basically trying to analyze every single path of the application, assuming the architecture that you are running on, and gives you an estimate of the worst case execution. Good. On the other hand, measurement-based timing analysis, well, based on exhaustive testing or statistical measurements. That's the empirical side of this. If I go to static timing analysis, this is the picture I was telling you, is that you can assume your application or task is split into what we call basic blocks. That's why I said some compiler technology is helpful, because all the compiler analysis is in fact done in splitting your code into basic blocks. Usually basic block in compiler terminology is a piece of code that does not have any jumps. Right? You don't, so it's within one function, it cannot span multiple functions. It does not have any for loops, for example. It does not have any if statements or jump instructions. So it basically is a procedural instruction. Why do I call it basic block? And why it's important for me? Because once you know that you never jump out of these instructions, once you enter your basic block, you know that all these instructions in this basic block will be executed sequentially, right? And hence you can estimate it. So I can, well, this is what static timing analysis do, is you split your code into different basic blocks, and then you can see here that there are branches and jumps based on, well, if statements, conditions, loops, instruction, function calls, whatever it is. And then I do analyze all of these and take the worst case path of jumps here, and then come up with, well, an estimate of the worst case section. For example, I look into these instructions. I know that the add takes 1 cycle, multiply takes 3 cycles, memory operation takes 100 cycles. I add all of this up, come up with a number in this basic block, another number here, another number here, here. And then I say, okay, for every single block, I have analyzed it separately. Now I want to come up with a number for the whole application. What do? Start from the beginning, take all the possible paths, add everything up along your way. This gives you one value of the computation time, and then take the max across all of them. This is, well, it's a simplistic view of how tools really run. They are much smarter than this, but that's the one way, in fact, to analyze things. Let me stop at that. That's very important. If you didn't get this, please ask, right? Because, for example, in the exam, I might give you an example tool and tell you, well, tell me the worst case time using static time analysis. And I give you estimates for every single instruction, how much time does it take. So you run by hand in a very simple example what a static time analysis tool might be doing. Does this make sense to you? So I run it in a 2-step. First of all, I divide and conquer. So basically, split my code into basic blocks. A basic block is series of instructions without any jump. Add all the execution times of the instructions, and then come up with that number. Now I have the array of numbers for every single basic block. Then the second step is, well, follow all the different paths, and then add things up along your way. For example, one possible path is this one. Another possible path is I go here, but then I come back at the beginning of this because this is a loop, for example. How many iterations do I run? Well, I don't know. Might depend on the index. If I have to take the worst case for numbers, right? And then I add them up, right? Does this make sense? Is there any question? Okay, so you can imagine how hard this can be. If you try to run this example for a very simple, this is a very simple tool, like I don't know, 20 instructions, maybe a little bit more, no function at all, support for loop statements. This might take you 1 hour, right? As a human being. If I have millions of lines of instructions and, well, thousands of paths, this might take days for a tool to run, right? So it's a very complex task to do. Why static timing analysis is in fact generally an incomplete problem. This is why people tend to go for measurement-based analysis. In a measurement-based analysis, well, industry calls this ABTA. You do a lot of measurements. I was telling you, you run it for millions of times. Well, Google car goes into the streets all the time. Tesla is still doing experimental stuff in Tesla owners, right? And then you basically try to do a lot of measurements under worst case scenarios, which what we do is heavy loads, for example, like a severe condition of weather or a lot of traffic along the way. And then data maximum plus a safety margin, what I told you is 10 to 15%. And this, because this is an empirical analysis, you assume you already run the exact actual hardware you need. For example, in a Tesla car, well, you are already using the Tesla, you're using the hardware. You don't need to model the architecture because you are already using the architecture and you collect the numbers, right? And this is a very common practice in industry, again, because of the complexity of static time. You see the difference between both statically analyzing the code and measurement-based one? Which one you think is in fact more safe? What do you think?
I guess I can go with this that.
Which one?
Static.
Static, yeah, exactly. And why is the case? Yes, exactly. So you don't depend on this, but rather depend on formal verification, right? So you go through all possible scenarios, then there are guarantees that in fact, analytical guarantees that in fact you have exhausted everything. In a measurement base, well, it depends on how good or how, what is the quality of your inputs, how many scenarios did you cover, right? So one advantage of static timing analysis, if it's possible, is in fact, it's much more safe. And this is why also certification authorities tell the people that if you do static timing analysis, your margin shouldn't be really too high. You can really have you can cut your margin, safety margin, because we are more convinced that basically the numbers you get is that the numbers that really make sense. Right? On the other hand, for measurement based, it's more practical, less safe, then my margin can be a little bit higher. Okay, one big problem with well, either static timing analysis or measurement based, for example, here, if I analyze this tool, we have ignored completely any other tasks in the system, right? I'm looking into the code of the specific task that I'm analyzing right now, right? This is assuming that the task is running alone in the processor, right? It does not access any shared resource. It's not being interfered by any other task. So, well, that's in fact not very convincing because we know for now that if I have a multi-core architecture, for example, or even a single-core architecture, that tasks would require access to shared resources like semaphores or critical sections. Well, the behavior of this task will depend on the other tasks running, right? So the problem even gets another dimension of complexity, right? So shared resources are big problems because, well, if you have shared resources, all what we discussed so far alone is void. We cannot really do it. We have to do a little bit more, right? But before we go into how to handle shared resources, because it will take us some time. What are some of the examples of shared resources? I already told you about critical sections of software resources. What else? What do you think, for example, might be shared resources in a test license? Well, we have already given the examples of IOs before, right? When we talked about shared resources and scheduling, we said accessing certain sensor, for example, the wheel sensor that goes into different tasks in the car, it's a shared resource. Yeah. Memory, exactly. Memory is another big resource, whether it's cache or a bus or an open-shared memory. This is in fact one of the most complex shared resources in a modern multi-core architecture. So if we take this picture that we had in lecture 1, which we already discussed. So if you have multiple processing elements, you have tasks that are running here. Well, they share, in fact, a bunch of hardware resources, including a shared interconnect a shared cache hierarchy, well, a shared memory controller and a shared official memory. All of these are shared resources that can cause interference and hence change the execution time of a task based on the behavior of other tasks running in the system. Okay? If you look closely into this one, every single red block here is in fact a source of interference. What do I mean by interference? Basically, contention between different tasks running. Because, for example, a task running in processing element 0 might want at one cycle to access the interconnect. Like if I go back to this example of code here, maybe at one of the instructions, I might have a load instruction. One of the basic blocks, I have a load instruction. Right? Load means I need to get something from the memory. How does really load work in hardware? Well, if I go here, assume our task is running processing element 0. I have a load instruction. I need to go to my private cache first. If it's a mess, I need to send a request in the interconnect that might be get from the shared cache or from the memory. Right? So a load instruction would go through, traverse this memory hierarchy. On the same exact cycle, so I have a multi-core architecture, another task running processing element 1 might also have a load instruction that also might want to access the interconnect. Well, interconnect is one resource. Can only serve one request at a time. Which one to pick? If I pick the request of task 1, well, I'm delaying this one. Or if I'm picking this one, I'm delaying this one. So there is an induced delay due to this interference. Why do we care about this delay? Because this delay will increase the execution time of the task. I have to account for it when I analyze because I want to make sure in worst case scenario, I will never exceed my deadline. Now the worst case scenario has a new source of complexity, which is the interference. Good. So is the story logical to you? Do you have any questions? Okay, so to give you a practical example, assume, for example, we have a dual core system, and then we have a last level shared cache. Well, here I'm using the avionics technology because I told you before, avionics require you to have partition systems. Every single partition is called the virtual machine, VM. A VM in avionics means, well, let's think of it as a separate core, for example. So it's a core that has its own resources and can be considered as a completely separate core environment. The problem is, assume I have two VMs, VMA and VMB, and assume that VMA running in one of the cores is running a safety critical task, like an airbag task, for example. And by the way, these slides are on Avenue. I see some of you are taking notes, so the slides are really not. And then assume that VMA is safety critical and assume VMB is not safety critical. It's running something like an infotainment unit in a car or an infotainment unit or an informatics task in avionics, for example. And then assume VMB suffers a cache miss, which means if I go to this architecture, assume this is VMB, this is VMA, I have a cache miss here from the non-critical virtual machine. And this cache miss, so think of, I hope you guys cover caches before VM, right? Some sort of, you know what is a cache miss, a cache kept, replacement policy? Yes or no? You know what? Can you give me an example for cache replacement policy, for example? What is even a cache replace? Let's go one step further. What is a cache replace? Some of you didn't take full VM. Oh, is that true? How many didn't take full VM? Oh, okay. Isn't full VM a two course?
Not for
I see.
Yeah.
Oh, yeah, I was not for land. Okay, I see. Okay. Okay, that's good to hear. So, well, thanks for letting me know, because from now on, I will assume minimum knowledge then for the end, right? So, if there's anything that I just came overlooked, just ask me live, right? Don't stay silent, just ask questions and I'll go through it. So, in a very easy high level, well, we use caching in modern architecture because caches are faster memories that are closer to the processor, right? This is really the essence. Main memory is well, something off a chip that takes a couple of hundreds of cycles to access. So our TLX, right? All of you guys might have seen a DEM before, right? You can really purchase discrete DEMs from Amazon, for example, right? They are in the range of gigabytes, 32 gigs, 128 gigs. Like something is very cheap but it's very slow in terms of access time. So what modern processors do, if you look into laptop spec, it will tell you, well, I have an 8 megabyte SD cache or a 4 megabyte L1, 4 megabyte L2, and maybe 156 L1. What does this mean? There is a cache hierarchy here. So between the processor and the main memory, I add a bunch of series memories that are faster to access. Why do I do this? Because caching is a very normal technique in even modern times. If you want to go to the library, then you want to read something about computer architecture, you will go to the shelf and then bring maybe 3-4 books, put them into the table and then sit down, open one. Once you are done, you close it, open another one. It doesn't make any sense that every single time you need a book, you go again to the shelf, bring it, and go back and bring it, right? You just basically save your time by bringing a whole bunch of data in one place, and then it's closer to you. It's faster to access. Good? So basically, this is a caching concept. The problem is cache is a smaller capacity compared to DRAM. I was telling you that modern DRAMs are, well, I know my laptop is 32 gigs, yours might be 64, or I know that there are some laptops right now 128 gigs. But your caches are maximum 8 megabytes, right? So something that is well, order of magnitude less in terms of capacity. So most of the time, what you are hoping for, or systems are designed that you will hit in the cache. It means when I have a memory load of store instruction, I'm able to get it from the cache. So it's much faster. Like L1 access latency is 1 cycle. L2 or L3 access latency is maybe 5 cycles. DRAM access latency is a couple of hundreds of cycles, right? So it's, again, an order of magnitude difference in terms of access time. So again, the hope is that 99% of the cases I'm hitting today. But what if there is a mess? If there is a mess, well, I need to go to the main memory, bring this data, and put it in the cache, right? Why do I do this? Because later on, if I need something similar, I access directly from the cache, right? The problem is because cache has smaller capacity, it might get filled in very quickly. So if you want to bring in something from the memory and put it in the cache, you might end up having a full cache. And hence we need a replacement. The replacement means I need to evict something from the cache and put a new line, right? This is why it's called replacement. You replace an old line with a new line. And this, well, it's a topic that takes 3, 4, 5, 6 lectures in a lot of papers done. There is a lot of complexity in that topic, but this is the essence of the intuition behind the idea. The problem is, and this is what matters for real-time systems, if you had a single task, people, static time analysis, they develop techniques that they are able to say, assume I'm running a single core, single task. Even with a cache hierarchy, people were able to determine by looking into the task pool, which one can be a miss and which one can be a hit, right? So for a single task, I can analyze the number of misses and number of hits. And then hence I have a reasonable worst case execution time. But if it goes to a multi-core with 2 tasks running, here I'm showing you the example, well, here in this slide. I guess I'll keep going back. Here I'm showing you that, in fact, a critical task, in our case, this is an VMA, can be impacted by the behavior of another non-critical task in another core. Why that's the case? Because of the cache behavior. So let's look into that architecture here and see the scenario that might happen. So I'm saying that VMB, which is I will call it non-critical and critical task, so just to simplify. So this is the non-critical task, this is the critical task. And here we have a shared cache between them. The non-critical task trying to access the shared cache, it doesn't find the data that it's looking for, so it's a mess. It has to go to the main memory, bring the data to the shared cache. Well, the shared cache is full. What do I do? Well, replace it, which means evict an old line. Do you see what the problem might be? This old line might belong, in fact, to the critical task, which means the non-critical task has evicted a line that was belonging to the critical task on the shared cache. Why that's a problem for execution time? Because originally, if I'm analyzing the critical task alone, I assume this line, if I have a load instruction, this line, it will be a hit in the shared cache. What is the hit? 5 cycle access time. I add 5 into my analysis and then do the worst case execution time. Right now, it's a mess. So it's no longer 5. It's a couple of hundreds of cycles with the DRAM. So the non-critical task impacted the behavior of the critical task, impacted the execution time of the critical task. Good? It's very problematic, right? It's very tough to do, right? That's why in earlier lecture I told you in avionics, they tell you if you want to have a multi-core, this example, you have to shut down one core completely at a time. No 2 cores can be running simultaneously. up until now. They're trying to simplify quality. The industry is going through a transition, both avionics and automotive, because of, well, we need multi-cores anyway. There is a lot of tasks to run. I cannot really afford shutting down all the cores. So they try to come up with some guidelines. And we will discuss some of these solutions right now, how to be able to, well, measure this interference, bound it, and hence we can reason about the execution time, even in the existence of measure. Good? So let me stop for a second and see if there is any question. I know that it's a lot of information, right? So you guys feel free to ask, right? Okay. So now I hope I kind of, given that you don't have a question, I convinced you that having shared resources in a multi-core system complicates the analysis a lot. So we have to account for. We already have taken the example of a shared cache. There's also shared main memory, shared I/O, interrupts, etc. So many critical sections or shared resources they can have access. How to accommodate for this? Well, one possibility to accommodate for this is to say, I'm going to expand my task model. Instead of saying worst case execution time is only related to the computation time of the task, which is what we have assumed in analyzing this, for example, here. All the assumption was that, well, I do all the computations, I measure the time, put it aside, add it up, right? So I'm only bounding the computation time in the core. Instead of this, I need to expand my worst case execution time to also include the access to the shared resource. So we would say worst case execution time now will equal to the worst case computation time. And this number can use the old method of analyzing the task in isolation, looking into the source code, add the numbers, come up with a number. But then you need to add another term to your worst case execution time, which includes the interference from different resources. This interference can be bounded by saying, well, for that task, I measure how many requests in worst case can access that resource. For example, I go back to my code, I count how many load and store instructions I have in worst case. Those are memory requests, which means they are accessing the shared memory. And then for every single request, I multiply it by the worst case possible latency, assuming maximum interference from all other ones, right? And then by doing this, well, I accounted for the shared interference in my worst case execution. Make sense? Okay, so what we're doing is we're extending the traditional model. Instead of saying we'll only have a worst case execution time, I'm splitting the worst case execution time into worst case computation time, which is basically a guaranteed bound in the core computation. Was add, multiply, divide instructions. And then there is also worst case number of requests for every single shared resource. And then the worst case interference from other tasks. And then again, my worst case execution time will be that summation of it. Good. And this basically takes us to the, well, subsequent topic, which is how to account for different shared resources in modern embedded systems. I will say I will give you 5 minutes break, and then I will switch to the slides. I will also upload the new slides. Okay. Take 5 minutes to refresh your mind, and then we switch to that topic.